That melody. I finally know where that melody's coming from. It's beating from the heart of hearts, the center of centers, the end-all, be-all of celestial bodies. And as its song rings out into the cosmos, I alone have tuned into it, and I shall listen to its symphony attentively and wholeheartedly. What's up? I'm Professor Milky, and I'm going to talk to y'all about black holes. So, what exactly is a black hole? Well, according to Wikipedia, a black hole is an astronomical body that's so compact that its gravity prevents anything, including light, from escaping. Though, just that on its own is pretty basic information. It's bland, narrow, and doesn't actually provide a thorough explanation as to what exactly a black hole is. How they work, how they're formed, and how they can function as more than just a compact body with an extreme gravitational force, which are the exact topics that I'll be diving into today. So, first and foremost, how do black holes exist? Like, how do they come into existence? Well, they mainly form when a supernova occurs. When a massive star dies out and collapses, they'll typically leave behind a body with a fraction of its initial mass before detonation, either between a neutron star and, if the star is large enough and explodes with such visceral force, a black hole. When a black hole forms, any celestial bodies around it are immediately absorbed by it, including other black holes that may merge with the newly formed one. Alternatively, they can form via the direct collapse of primordial gas clouds, causing a supermassive black hole to form. These kinds of black holes are typically referred to as direct collapse black holes, or DCBHs, in which the process of creation involves primarily gas and does not involve the event of a supernova. Well, now that we know how they can appear, it's time to dissect one and explain how each bit of it works. Let's start from what's furthest and work our way from there. The accretion disk, the giant ring of light that surrounds most black holes when they aren't invisible to the human eye, is a large ring of gas that surrounds the circumference of a black hole before slowly being pulled into it to increase its mass. When black holes absorb other bodies into itself, the terminology used to refer to that is called accretion, when a mass absorbs other masses gradually over time to become something larger. The far sides of the disk, both at the top and bottom, are warped due to the photon sphere of the black hole it's surrounding. The innermost stable circular orbit, or ISCO, of a black hole is the distance at which a particle can stably orbit around the black hole. If any outward perturbations influence the orbiting particle, then they'll either, depending on the energy, spiral into the black hole, pull away into a stable orbit, or escape into infinity. A perturbation is any form of outside influence that may deviate a system's state, movement, or path. The shadow of a black hole, also known as the ergosphere, is the part of the black hole that essentially blocks out all light that passes into it, causing whatever light rays that hit it to reflect off of its surface, alongside being the sole force that slowly pulls matter into it beyond the event horizon. This bit leads me into the event horizon. This is what gives it its insurmountable gravitational pull on any form of matter that dares to come near it. When objects pass the ergosphere and enter straight into the threshold, that's when they essentially cease to exist and inevitably become one with the black hole's total mass. And if any form of living matter were to somehow cross into it, the required escape velocity would need to be faster than the speed of light. So if you're in something that's somehow capable of exceeding 300,000 kilometers a second, be my guest. At the center of a black hole lies its singularity, the final destination for anything surrounding it, crushed down to infinite density and absorbed by the black hole. Unlike everything else, this part of it isn't all that interesting. Now, what exactly is their place in the solar system outside of just being really hungry? Despite their role being drastically changed, they're still stars, but now they're just really massive, typically weighed in solar mass. Actually, now that I think about it, solar mass is an entirely different can of worms I gotta open up for this to make sense. Stars, as a celestial body, are measured by solar mass, which as a general constant is roughly 2.0 times 10 to the 30 kilograms, or in more exact terms, 1.988416 times 10 to the 30 kilograms. The exact mass given is what's supposed to be the estimated mass of the Sun. The average mass of a black hole depends on its classification. The smallest, being micro black holes, can be about the same mass as the Moon, or 7.346 times 10 to the 22 kilograms. Standard stellar black holes can range from 2 to 150 solar mass. Intermediate mass black holes, or IMBHs, can range from 10 to the 2 to 10 to the 5 solar mass. Anything past this is classified as a supermassive black hole, SMBH, around 10 to the 6 to 10 to the 9 solar mass. Or an ultramassive black hole, UMBH, at around 10 to the 9 to 10 to the 11 solar mass. So on average, most black holes are around 100,000 times as heavy as the Sun. Now that that's out of the way, time to explain how else these dark behemoths can function. At the center of the Milky Way is a supermassive black hole, Sagittarius A, weighing in at 8.54 times 10 to the 36 kilos, or 4.297 times 10 to the 6 solar mass. Everything surrounding it is rotating around it, including the Sun and the planets that encompass it. As it stands, this singular black hole from the Earth indirectly is about 26,996 light-years away, with a 33 light-year margin of error, or in a shorter form, around 8,277 parsecs away, with a 9 parsec margin of error. A parsec is essentially what a yard is to a foot. Much like how a yard is 3 feet, a parsec is 3.26 light-years. Much like accretion disks orbiting around black holes and planets orbiting around the Sun, everything within the Milky Way orbits Sagittarius A due to their immense center of mass that essentially made it sink to the bottom of the gravity well, which now makes it the sphere of influence for the entire galaxy. Other examples of systems orbiting around the black hole include Tonnenzintlus 618, or just TON 618, and the Phoenix Cluster, amongst literally every other galaxy, in which their galactic engines are both supermassive black holes that drive everything around it. Alright, final segment, because I'm getting bored of this and you might be as well. I'm going to go over 2 separate pieces of terminology used in the study of black holes, those of which being redshift and Schwarzschild. Gravitational redshift, otherwise known as Einstein's shift if you look at older texts and papers, is the phenomenon in which electromagnetic waves or photons traveling out of a gravitational well lose energy. If you were to observe an object that's on a course to a black hole, the moment it enters its ergosphere, 2 things will happen. 1. Beforehand, the object from your point of view will begin to slow down exponentially before coming to an abrupt stop. Because of the black hole's intense amount of gravitational pull, it curves space-time in such a way that it affects all measurements of time and space the closer you get to a black hole. This is what is known as time dilation. 2. This is the main focus of the explanation. After a while, the object's color begins to slowly shift more and more red because the electromagnetic waves bouncing off of the object are beginning to lose energy since the object's already so far down in the gravitational well. And soon, the object vanishes due to it being so intensely redshifted that it can no longer be properly observed. To calculate the gravitational redshift associated with a photon traveling in a gravitational field of an uncharged, non-rotating, spherically symmetrical mass, otherwise known as a Schwarzschild black hole, the following formula required is 1 plus z equals 1 over the square root of 1 minus 2gm over rc squared, in which z is our redshift, g is our gravitational constant, m is the mass of the object, r is the radial distance from the center of mass or the source, and c is the speed of light. This equation utilizes what's known as the Schwarzschild radius, in which rs equals 2gm over c squared. On that topic, Schwarzschild. The Schwarzschild metric, created by German physicist and astronomer Karl Schwarzschild, is an exact solution to Einstein's field equations that describes the gravitational field around a spherical mass based off of the assumption that it has no charge, no angular momentum, and no cosmological constant. A Schwarzschild black hole, which follows the Schwarzschild metric, has no rotation and no charge. Schwarzschild black holes are typically used to calculate how far the event horizon is from the singularity, which, as previously mentioned, is as follows. Rs equals 2gm over c squared, in which, as previously mentioned, Rs is the Schwarzschild radius, or how far the event horizon is from the singularity, g is the gravitational constant, m is the mass of the black hole, and c is the speed of light. I think I covered everything, or I at least covered the basics of what a black hole is outside of funny gravitational thing that eats a lot. Now if you excuse me, I'm out for lunch. Toodles!